All right, Physics Nerdies, how's it going? So today we are going to talk about decay chains. Okay, so the whole idea of decay chains, I'm not going to watch this one, it's kind of a lame decay chain. I have a different app for this one, is that the decays that are happening are trying to get the parent particle to this black line. So you're all in this blue radioactive area here, they're undergoing decay, and they're always trying to move towards this black line by removing protons, adding protons, just trying to get its way to this point. Now, usually when we're talking about this, talk about decay chains. Some decay chains take a lot of paths to get to where it needs to get, and sometimes they're not all set. So if I go to the last slides here, it doesn't really matter what's on this last slide anyway. So you can see one here, that uranium-238 could take multiple paths and end up at the same point. And they're trying to get to this stable element. In this case, lead-206 is a stable element. Lead-210 is not stable, and lead-214 is not stable, but eventually it gets to this lead-206. But it could take multiple paths. And you can see that from this app here. So we're going to do, which one are they doing here? Uranium-238? Do I have that one? Oh, wait, right here. All right. So you can see down here, uranium starts off uranium-238, undergoes alpha decay, becomes thorium, then undergoes beta negative, becomes protactinium, beta negative. Beta negative is the more common version of this. Beta positive it's in nature, like I was saying, bananas have beta positive in them all the time. If you eat enough bananas, you get them radioactive. Oh, so you can see it's changing, it's getting closer and closer to that stable isotope of lead. Well, you notice it got to lead, but it's not stable. And you can see here, it branches out. When it gets to here, it can either go to beta negative or go alpha, then beta negative, beta negative, beta negative, alpha, or beta negative, alpha, beta negative, beta negative, alpha. Right? So there's lots of different ways. In this case, there's really only two ways to get to where it needs to get to. Other elements, like let's say Neptunium here. Starts out down here. It's actually plutonium. Beta decay, and this little chart that I'm covering up here, these are all like the half-lives. How long does it take for this to actually happen? Some of them pretty long. Okay, here we got 14 years. Uranium-233 is pretty stable. It's 500,000 years for that to actually happen, undergo beta or alpha decay. Right, here's another one, 2 million years for Neptunium to do what it needs to do, Neptunium. Some of them are really small, 32 milliseconds for this to happen, right? And then go down a bit further. There's a couple of there's another microseconds there. This is gigantic here. Bismuth 209. Is that on here somewhere? 209. Way up here. Is that the stable element? No, it's not the stable element. The most stable element in this case is thallium. Thallium 205. You can see it doesn't have a half-life here. It's a pretty stable element. But again, it takes multiple paths. It takes lots of ways to get there. It's always trying to reach that stable element at the end. That's it. That's all I wanted to show you with that. Yeah, you undergo alpha, beta all the time. In this case, most of the time, you're still going to see alpha decay and beta negative decay. But on the rare occasion, you'll get beta positive decay happening as well. Okay, so I'll see you next week, the last week of lessons, and we'll talk about half-lives, like I was saying, those half-life numbers. Fission and fusion, more mass defects, more energy being released, and I'll see you then. Bye.